We went over these rules for series and parallel circuits, but just to refresh. For series circuits, there's only one path for electricity to flow, and that is why the current is the same in all places. It's like a hose or a pipe. Solid pipe might be a better way to think about it. Whether the pipe is wide or narrow, whether there's resistance in one part or another part, the flow rate has to be the same everywhere in there. Otherwise, it wouldn't be called current. To find the total resistance for resistors in series, we simply add up all the individual resistors. Voltages, or potential differences, across devices, such as resistors or light bulbs or motors or things like that, are things that add up. So V1 plus V2 plus V3 equals V total provided by the circuit. So the battery, which is represented by a long line and a short line, this side being positive, this side being negative, is something where that provides a certain amount of energy per charge or potential difference, and it's used up or converted into other things other than electrical energy, into things such as heat and light across the resistors. Whatever is provided in any loop by the power source has to be used up in that loop across the resistors. So brightness depends on power. P equals V times I, and there's a couple other ways to calculate that. Ohm's law is the formula we use mostly for solving things in terms of circuits, voltages, resistances, currents, and it works for any whole circuit or any part of a circuit, whether that be parallel, series, or combination. For parallel circuits, the current in each branch, well, there's multiple branches for each of these circuits. And in each branch, there's an individual current, and the sum of those currents add up to the total current provided by the power source. The voltage across each parallel branch has to be the same. Why? Because it's the same drop or difference in energy per charge. So it's kind of like if you're at the top of a mountain, you could head down a number of different paths to the bottom of the mountain, but whichever path you choose, you change the same elevation change. It might be a steep path or a shallow path, but if you start at the top and end at the bottom, you've had the same change in elevation. Here we think of that as the same change in potential energy per charge. Resistance, this is the toughest part mathematically, I think. So when we figure out resistance for parallel resistors, we have 1 over the total resistance equals 1 over the first plus 1 over the second plus 1 over the third. So you've got to know how to use the reciprocal or x to the negative 1 button on your calculators pretty well. As an example, if I have two 12 ohm resistors, that would be 1 over 12 for resistor 1, 1 over 12 for resistor 2. That equals 2/12 or 1/6. 1/6 is not my total resistance. 1 over my total resistance is equal to 1/6. So my total resistance is 6. So for parallel circuits, every time you add a branch, the resistance goes down, unlike for series circuits, whereas every time you add a branch or add a resistor in series, the resistance goes up. Why does the resistance go down when you add a new branch with a resistor in it? It's because we have more paths for the electrons to flow. So if you have more paths to flow, more electricity will flow. If you haven't affected the other branches at all when you add that extra path, then you simply add the amount of current going through the new path to the amount of current going through the other paths to find the total. So if you're adding more current, you're effectively lowering resistance. So I'm going to go through the examples to these a little bit. This is a series circuit, and this will be a parallel circuit. This will be a combined circuit where we have one resistor in series and then 2 in parallel and then another one in series. And then here's one where we've got 2 in parallel, 1 in series, and then kind of a mess down here. A key thing is, I think, drawing simplified diagrams. So when I look at this one, I've got 4 resistors in series. So the first thing I need to do, usually with circuits, is find the total resistance. So for a series circuit, I just add them up. 3 plus 8 plus 12 plus 1 is 24 ohms. The current, I'd use Ohm's law, V divided by R, 24 volts divided by the 24 ohms, that's 1 amp. The current has to be the same at all places here. So I've drawn letter A and letter B showing two locations where we could find the current, where we would put an ammeter, which measures current, into the circuit. And both those would be 1 amp, no additional calculations. We hook voltmeters across or in parallel with electrical resistors because we want to find the difference in potential energy from one side to the other. So we can't hook an ammeter in series like we would, or a voltmeter in series like we would an ammeter. So to find the voltage across each of the resistors, I need to know the current going through each resistor and the resistance value of that resistor. Well, that's easy here because the current going through all the resistors is 1 amp, and the resistance values are shown. So it's simply I times R, I times R, I times R, and I times R. So notice that in this particular case, all these voltages used up, or these drops of potential difference across the resistors, that's 8 plus 12 plus 3 plus 1 equals 24, which is the total voltage that was provided by the power source. To find the power rating of the circuit, we simply use V times I. So that's the total voltage multiplied by the total current, so that'd be 24 watts. For circuit 2, this is a parallel circuit. It's got 3 branches, one with a 5 ohm resistor, one with a 20 ohm resistor, and one with a 4 ohm resistor. The power source has 36 volts. So the first thing I want to do is I want to find the total resistance of the circuit. The way I can do that is add these in reciprocal as noted up here for parallel circuits. So I have 1 over 20, so it doesn't matter the order, 1 over 4 plus 1 over 20 plus 1 over 5 equals 1 over R. Well, add all those up, I get 1/2. But my resistance isn't 1/2 because 1 over the resistance is equal to 1/2. So the total resistance is 2 ohms. To find the total current in the circuit, meaning the total current leaving the power source, take my total voltage of 36 volts divided by my total resistance of 2 ohms, I get 18 total amps is leaving this power source right there. So that's kind of what's happening right there, 18 amps. Part of that's going to go down here, here, and here. These parts are just showing where I would put voltmeters. That one kind of got cut off a little bit. So I'll put that over there. So this would be 36 volts across the power supply. If I look in any path, in this case, the only place where I have resistance, and I'm assuming these wires are ideal wires, is across the resistors. So therefore the voltage across voltmeter 1 is 36 volts, and the voltmeter across voltmeter 2 is 36 volts, as well would be the voltage across each of these resistors. So we don't add up voltages in parallel because each path is independent. And in each path, the charges have to lose the full voltage of the power source. So now to figure out this voltage, I've got a wire with no resistance, so 0 ohms times whatever current would give me 0 volts. To find the current through these, what I end up looking at is this voltage divided by this resistance, 7.2 amps, this voltage again, the total divided by this, 1.8 amps, this voltage divided by this, again, 9 amps. So when I add all those up, 7.2 plus 1.8 plus 9, I get 18 amps, which is what I thought I would have when I just did the total voltage divided by the total resistance. So it's a nice double check. Here, to find the power of the circuit, total voltage multiplied by total current, 648 watts. I'm going to go through this. It's the simplified, it's a combined circuit with some parts in series and some parts in parallel. So the first thing I want to do is solve for the total resistance, but to do that, I've got to solve the equivalent resistance for this part of the circuit. So basically I'm putting all these things together to find one equivalent resistance, and then I'm going to break them back down again to figure out what's going on in each specific part of the circuit. So here I've got a 6 ohm resistor and a 12 ohm resistor in parallel with each other. If I use the rules for figuring out parallel circuits, 1 over 6 plus 1 over 12 equals 1 over R. 1 over R is 1/4, so R is 4 ohms. So this part of the circuit is 4 ohms. Now, when I look at that, I can treat this as a single 4 ohm resistor. So I would ask you to redraw the circuit here with a 3 ohm resistor, a single 4 ohm resistor, and a 5 ohm resistor. When I do that, I get 3 plus 4 plus 5, which means my total resistance is 12 ohms. Total current, 6 volts divided by 12 ohms is 0.5 amps. So if I want to think about the next thing to attack, I would attack the voltage across each of these resistors. So 0.5 amps is going through here times 5 ohms is 2.5 volts. 0.5 amps times 3 ohms is 1.5 volts. Now I know the battery is providing 6 volts, so there's a couple ways I could figure out the voltage across V2. I could use my other picture and think of this as a single 4 ohm resistor. 0.5 amps times 4 ohms is 2 volts. Or I could recognize the fact that 6 volts is the total provided. I use 2.5 across this resistor. I use 1.5 across this resistor. I could subtract those off from 6. 6 minus 2.5 minus 1.5 also gives me 2 volts. So the voltage across either of these two resistors in this path would be 2 volts. Now that I've got the voltage here, I can go back and figure out the current. So the current, which is 0.5 amps total, is going to split up. More current will go down the branch with less resistance. Less current will go down the branch with more resistance. Since this is twice the resistance value of this side will have twice the current value of that side. However, the total current through both sides have still got to equal 0.5 amps. So since I know that I've got 2 volts across here and 6 ohms, 2 divided by 6 is 0.33 amps. 2 volts divided by 12 is 0.167 amps. Notice when I add those up, I get 0.5 amps, which is my expected total. I'm going to leave this one for you to think about and do because I think it's kind of important that you look through how to do those, but I will leave the PDF.